This year's rover integrates upgraded mobility, communications, manipulation, autonomy, and science into a competition-ready system focused on efficiency, performance, and reliability.
The drive system now runs custom low-latency control loops between each motor driver and the rover PC, resulting in faster feedback, active traction control, and braking. Instead of relying on open-loop throttle inputs, we modulate torque directly, resulting in smoother acceleration, more predictable deacceleration, and improved performance across rugged terrain. To assist the delivery mission, we integrated a custom quadcopter drone. With a 23-minute flight time, the drone supports a stabilized camera payload mounted on a two-axis gimbal, enabling independent pitch and yaw control for continuous target tracking and horizontal stabilization. The drone streams live video directly into the base station UI, allowing operators to assess terrain, identify targets, and plan approach paths.
We implemented the mast that supports a new dual-band radio architecture using a 900 MHz link for primary control and H.265 video feeds, alongside a 2.4 GHz link for additional high bandwidth. Structured range and interference testing were conducted to validate stability under varying terrain and line-of-sight conditions, ensuring reliable operation during competition-scale missions. We built a custom web application that consolidates heading, GNSS position, velocity overlays, and live subsystem diagnostics into a single operator interface, improving operational clarity and mission efficiency.
The rover is equipped with a 6 degree of freedom dexterous robotic arm mounted in the forward payload bay. This year, the arm features a redesigned wrist and end effector with an integrated camera and solenoid actuator. The manipulator demonstrates its ability to complete all servicing tasks required for this year's competition, including manipulating switches, panels, test tubes, and drawers. The new wrist design utilizes a differential drive gear system to enable smooth pitch and roll rotation while minimizing volume and mass. By adding a slip ring between the forearm and wrist, we achieve continuous roll without cable constraints. This expands the manipulator's range of motion and improves user operability during missions. The new end effector incorporates a rack and pinion transmission, alongside optimized finger geometry and texture contact surfaces for a stronger grip. We implemented inverse kinematic control modes using Move It Servo to enable Cartesian end effector control. Operators can switch between joint space and Cartesian control modes depending on task requirements, improving usability and precision during fine manipulation. To enable autonomous typing, the integrated solenoid is guided by the wrist camera and a forearm mounted RealSense stereo depth camera for visual feedback and key localization. This dual camera configuration improves depth perception and reduces key targeting error.
We transitioned the autonomy stack from a custom implementation to Nav2, standardizing planning and recovery behaviors while improving long-term maintainability. We localize using a 15-state extended common filter that fuses dual antenna GNSS, an 9-axis IMU, and wheel odometry to produce continuous pose estimates in the odometry frame, enabling smooth path planning and stable trajectory tracking. Global planning runs on Nav2's hybrid A-star planner over a layered cost map, generating smooth paths that respect the rover's motion constraints and surrounding obstacles. We retrained our YOLO V11 perception model to include the new object class and run it on the rover PC's integrated GPU, achieving up to 40 frames per second across combined streams. Perception, planning, and control are able to run concurrently without saturating system resources, enabling reliable autonomous execution under mission load.
We integrated additional soil and atmospheric sensors and exposed them through the rover web interface for real-time monitoring and structured data logging. Sensors onboard the rover test for humidity, temperature, conductivity, pH, nitrogen, phosphorus, and potassium. Soil is ejected from the drill until the desired depth is achieved, at which time soil is redirected to a sealable, removable cache, which remains uncontaminated. Chemical analyses will be done with scooped surface samples. The chemical suite now includes an additional row of tests for each site of interest as an additional method of life detection. 3 assays are analyzed using a UV spectrometer, and one is evaluated with an in-suite camera. The sulfide test is assessed semi-qualitatively using a standardized color chart. The bisynchronic acid assay measures total protein concentration analyzed at 562 nanometers. The molybdenum blue assay quantifies inorganic phosphorus, analyzed at 660 nanometers. The dinitrosacylic acid assay detects reducing sugars, analyzed at 540 nanometers. Calibration curves for all 3 assays have been refined to improve quantitative accuracy.
We will be continuing to validate the rover through integrated field testing and full mission rehearsals under representative operating conditions. All subsystems are competition ready, and we look forward to demonstrating our new capabilities at URC 2026. Thank you to all our sponsors who have supported us through this design cycle.